My name is Hale Farley. I'm a volunteer at Vintage Tech, working remotely in California. The graphic storage terminal needs a device for hard copy output. Tektronix designed a special one-line CRT, which is shown setting in the paper tray. Similar to the photographic process, it exposes 3M dry silver paper and was thermally developed to produce quality hard copies. While we have a functioning hard copy unit at the museum, the supply of the dry silver paper is long obsolete. The one-line CRT was unique in that the faceplate was made of fiber optics. It had the effect of transmitting the image, which was formed on the phosphor deposit on the inside of the tube, to the front side of the faceplate, so no lens was needed to project the image to the paper. The paper traveled directly over the faceplate for exposure. Introduced in 1975, the 4051 was an evolutionary product following the calculator. An early scientific workstation, it combined 11-inch storage display with a programmable microprocessor. The programming language was BASIC with extensions for graphics. High-precision floating point computations were a feature fitting into the requirements of the scientific and engineers. The ability to produce high-resolution graphics, 1024 by 768, allowed the analysis of results on the same device. This resolution was not matched until much later. Memory available started at 8 kilobytes with a maximum of 16 kilobytes, a large amount for the era. Program and data storage on a magnetic tape cartridge made specifically for digital data. It had a capacity of 300 kilobytes. The workstation featured a general-purpose interface bus. This was an early interface for communication between computers and multiple instruments or peripherals. It vastly expanded the capability of the 4051. The basic language also had extensions to communicate with attached peripherals. Expanding 4051's functionality could be done either by software stored on magnetic media or a ROM pack. A wide range of applications were available for both media. Additional interfaces to other devices, such as a printer, was also available through ROM packs. The 945 oscilloscope is a 545 oscilloscope that was designed to meet military and environmental specifications for use in extreme conditions. It is designed for increased shock, humidity, temperature, and vibrating conditions. It's also more shielded for interference from radio frequency interference. The plugins have a more robust latching mechanisms, and the vacuum tubes have physical hold-downs. There is a seal cover for the front and the rear of the instruments, and the B and C connectors all have covers. The size and shape of the instrument was designed so it would fit through a submarine hatch, a requirement that many standard products were designed to meet. The first 3 945 orders were shipped in April 1961 to Bell Telephone Laboratories in New Jersey. The price was well over twice that of the 545 oscilloscope. Customers eventually decided that the well-designed standard Tektronix products could meet most of their requirements. The only other recognized standard product that we know of is the RE4012, which was a 11-inch graphics terminal also designed for harsh environments. The 555 was the first dual-beam oscilloscope designed by Tektronix and was introduced in 1959. It is a very large instrument consisting of a display unit that is shown and a separate power supply. A standard 2-channel oscilloscope has a single beam CRT that displays 2 waveforms by either alternating or chopping the vertical signal. Alternating draws one trace, then the other, which works well at high frequency. Chopping draws short segments alternating between both waveforms, which works well at lower frequencies. The horizontal time setting is common for both traces. As such, you cannot view two signals of unrelated frequencies. A dual beam CRT is designed with two completely gun assemblies, so the resulting instrument is fundamentally two complete oscilloscopes in a single package, sharing the power supply and screen. The 555 oscilloscope is unique in that it also features dual horizontal plug-ins, the only Tektronix scope with this capability. Since 555s were mounted on the 500 series scope mobiles, providing some amount of portability for the instrument. These oscilloscopes are commonly called clones, but in fact they were instruments made by Hitchcock, Tektronix, and Lovey. In 1959, the Air Force awarded contracts to Hitchcock for oscilloscopes equivalent to the Tektronix 545. A Tektronix field engineer who saw a pre-production model reported that this was a modified Tektronix scope which had been disassembled, rearranged internally, and put back together again. When Tektronix learned of the 545 contract, they contacted these companies, warning them that these instruments were infringing upon Tektronix patents. These conversations ate up months, and by 1960 had exhausted any hope of settlement. In January 1961, Tektronix retained a legal firm to pursue the case against the U.S. government. A suit was filed the following month where Tektronix alleged that the U.S. government had given other firms contracts whose specifications were for the manufacture of Tektronix oscilloscopes. Soon after Tektronix had filed lawsuits, the U.S. government filed a counterclaim against Tektronix alleging infringing on two government patents. The court dismissed the government's claim and the trial ended March 4, 1966. The U.S. Court of Claims Commissioner indicated it would require up to a year to study the case before making a final judgment. It took until May 1970 before the commissioner ruled in favor of Tektronix. In 1979, almost 18 years after Tektronix first filed suit, Tektronix versus U.S. et al. Came to an end with a judgment of just over $4 million. Shown here is a Tektronix oscilloscope with Hitchcock plug-ins. Tektronix management first thought about some type of venture in Japan in the late 1950s, as they wanted direct presence in Japan. By 1963, Tektronix began conversation with Hitachi and Toshiba. While in Japan, Howard Vollum visited Sony and was impressed with their chief engineer. In 1964, Earl Wantland visited Sony to further discussion, and in March 1965, Tektronix and Sony struck a 50-50 partnership called Sony Tektronix. Sony Tech began operations in a Sony building in Osaka. They began by building products using Tektronix assemblies and later developed their own products, usually focusing on miniaturization and specialization for the Japanese market. Sony Tech built their own facility in 1969 and in 1976 expanded with a new manufacturing facility in Gothenburg. In 1980, they expanded with an 8-story building next to the original building. We have a number of Sony Tech products on display at the museum. This Sony Tech 335 35 MHz dual trace oscilloscope was a very popular instrument. Sony Tech engineers would work with Tektronix engineers to design their own CRTs, which was typically manufactured by Sony. For more than 35 years, Sony Tektronix was an integral part of Tektronix global strategy. In 2002, Tektronix acquired Sony's interest and the resulting company became Tektronix Japan Limited. From the founding of the company, Much of the internal test equipment Tektronix used was designed and built in-house. Tektronix continued to design and build internal test equipment if they could not acquire either what they needed. This 130 LC meter is an example of one of their internal designs that later become a product. It was first introduced in 1954 for a selling price of $195. It continued for 21 years and made its last appearance in the 1975 catalog for a selling price of $400. We believe it was the longest running Tektronix product. The Type 130 was designed by Cliff Moulton, who started at the Hawthorne plant. The 130 underwent several facelifts with essentially the same circuitry. The museum has both an early brown louvered cabinet and a later traditional blue-sided panel 130. These instruments are still sought by collectors for their usefulness and reliability. One of the key specifications for an oscilloscope is bandwidth, which represents the highest frequency signal it can acquire and accurately display. For signals with even higher frequencies, a sampling oscilloscope collects samples from successive cycles and assembles them to show a complete image of the waveform. They can display much greater frequencies, but require repetitive signals, so they cannot display one-time or single-shot events. The Type N sampling plug-in was designed for the 500 series oscilloscope by Norm Winningstaff and was introduced in 1960. The plug-in drives the oscilloscope in the XY mode. The N plug-in is fairly simple, with a fixed sampling rate of 100 kHz, fixed vertical of 10 millivolts per division, and no delay line. The Type N plug-in was soon replaced by a more advanced 661 sampling oscilloscope the following year. The museum has a Type N plug-in on the exhibit, which is displaying a sub-1 nanosecond rise time. This specific N plug-in was owned by designer Norm Winningstaff. Norm went on to head the Information Display Division, the first non-oscilloscope division at Tektronix. The delay line is used in an oscilloscope to view the leading edge of trigger events. The trigger signal is derived from the vertical signal path. The trigger and the sweep circuitry needed about 60 nanoseconds to start, so there is no display of the signal during this time. A delay line in the vertical signal path after the trigger signal will result in the ability to display the trigger portion of a signal. The Type 113 was a large standalone suitcase-style 50-ohm delay line introduced in 1960 to augment sampling applications such as the Type 110 pulse generator and the Type N sampling plug-in. The 113 continued into production until 1973. The actual delay line, called spiral line, was not manufactured by Tektronix. It was so named because the large semiconductor, about the size of a pencil, was held in place with a spiral of polyethylene tube. Tektronix would roll a spindle line into a coil and add the connectors as seen in this inside photo. Curve tracer are electronic instruments similar to oscilloscope. These instruments are used to display characteristics of active devices, tubes, transistors, diodes, and other devices. The instrument operates by varying a parameter and showing the resulting voltage and current characteristics. The parameter is varied in steps resulting in multiple traces, seen here in this photo. The first Tektronix curve tracer was a 570, introduced in 1955 to display characteristic curves for vacuum tubes. Two vacuum tubes could be inserted in the test fixture with the jumper cables to accommodate the various pin-out connections. Only one tube could be displayed at a time, but a switch could alternate between the two for comparison and matching of tubes. These curve tracers are still highly sought out by audiophiles for tube matching and command high price. The 570 was the only Tektronix curve tracer used for measuring vacuum tubes. All subsequent curve tracers were designed for measuring semiconductor devices. Tektronix produced a series of books for instructions on the design of oscilloscopes and making measurements. The Semiconductor Device Measurement Concept Book, printed in 1968, is devoted to curve tracer measurements for a variety of devices. This book is available used or as a PDF on our eBay store. The 576 is considered the ultimate Tektronix curve tracer. It was introduced in 1969 and featured a novel display readout using fiber optics and incandescent bulbs to display key operating parameters directly. These readouts allowed setup information to be captured in a screen photograph along with the display. The 576 can deliver 220 watts of power to the device under test with voltages as high as 1500 volts. There was a protective cover over the device under test with a safety switch for elevated voltage. The 576 was phased out in 1978. Tektronix continued to produce curve tracers until the mid-1980s. Sony Tektronix had also developed curve tracers and continued to manufacture them for some time. Analog television signals are a challenge to view on an oscilloscope. The 524 contains circuitry needed to identify the timing information irrespective of the video contact for ease display. Cliff Moulton designed the 524, which was essentially added to the 514 oscilloscope. In the 1950s, video signals were generated with analog circuitry dependent on resistors, capacitors, and vacuum tubes, resulting in a less than stable system. The 524 features time marker generated by relatively stable LC ringing circuits to ease the measurement of sync and blanking pulse widths. The 524 also had a line selector whereby individual lines in a field or a frame could be examined. The 524 was the first instrument in a long family of instruments for the television market. The 524 oscilloscope was easier but still challenging to operate and provide limited information. The waveform monitors are a specialized oscilloscope used to display television signals in the studio and at the transmitter. The 525 was the first waveform monitor that Tektronix produced, first appearing in the spring 1955 short-form catalog. It was probably not a coincidence that the 525 was named thusly, since the number of horizontal lines per field in the US TV standard was 525. The 525 was the first in a long line of television waveform monitors.
This is Kurt Kruger, a former Tektronix employee and now a volunteer for the Vintage Tech Museum. In 1955, the National Television Standards Committee issued a standard for a compatible colored television system, an enhancement of the earlier 525 line monochrome system. In 1956, Charles Rhodes, who had recently joined the company, started to work on a specialized oscilloscope called the Vectorscope. The color signal can be represented as containing three components: the brightness and two color difference signals. The Vectorscope display mode is an XY display of the color difference components, conveying color information about each point in the raster. The 526 did not display brightness. That was a job for the 525. Sales of the 526 began at a brisk pace in 1959, but began to taper off as customers began to witness the poor performance and stability of the first generation color equipment. Tektronix Vectorscopes, which enabled the precise measurement of color television signals, are credited with advancing the U.S. color television industry by several years. The National Academy of Arts and Sciences awards technology and engineering Emmys to organizations and individuals for breakthroughs in technology that have a significant effect on television engineering. Tektronix instrumentation significantly helped advance the U.S. television industry, and this was recognized in 1976 with their first Emmy. The Emmy was awarded for leadership in development of equipment for verifying television performance in the vertical interval. Tektronix and the subsidiaries, including the Grass Valley Group, Dubner, and Lightworks, received a total of 12 Emmys. Tektronix's second Emmy, awarded in 1984 for continued technical excellence and leadership in television test, measurement, and monitoring technology, is on display at the museum. It is popular for many selfie photographs. The Grass Valley Group was formed by Donald Hare in 1959. In the mid-1960s, they began to design equipment for the television industry, beginning with the Model 700 distribution amplifier. They soon expanded their product family, and in 1974 were acquired by Tektronix. They continued to expand their facility in California as sales grew. It was once said that any television signal you saw passed through a Grass Valley Group product. Shown here is a Model 1200 production switcher. Grass Valley switchers all have a famous T-handle for smooth control for effects and fade. The T-handle was used as a prop in the first 1977 Star Wars movie. A Model 1600 switcher was used as a firing mechanism on the Death Star. This was highly amusing to everybody in the switcher group. Tektronix needed precision signal sources to generate color television signals at a number of different worldwide standards. In order to develop PAL format, they needed a PAL signal generator. This proved difficult to purchase and had long lead times, so the team developed their own. The team found out that purchased television signal generators didn't perform very well. This provided an opportunity to enter the market with precision signal generators and expand the television market segment. They also developed precision television monitors for viewing the final signal. Together with waveform monitors and vectorscopes and other specialized instruments, Tektronix products were widely used in television studios and broadcast facilities to ensure the highest quality broadcast signal. Machine control, also known as numeric control or computer numerical control, is the automated control of machining tools such as drills, boring tools, or lathes by means of coded programmed instruction. Once the coded program instructions are loaded, a machine can process the material to specification without an operator. Tektronix started building machine controls in the late 1960s for its own internal use. Existing controllers available were large, often using tube circuitry which required frequent maintenance and were hard to maintain. Tektronix also developed a verification instrument for the program tapes. The program was punched onto a paper tape and the accuracy checked by viewing the toolpath on a 611 display. The results were a superb system, and a new market for Tektronix opened up. The 1701 and 1702 machine control units were introduced in 1970. Shown here is our 1703-2 machine control unit. This particular model was never released into production. Tektronix phased out their machine control products by the mid-1970s. The 321 oscilloscope is a very compact single-channel 5 MHz oscilloscope introduced in 1960. It is mostly a solid-state design with peanut tubes for the vertical input. It would operate on AC, DC, or tin D-sized nickel-cadmium batteries. Such a small portable oscilloscope garnered a lot of interest from a number of different applications and markets. One unique application was identified in a flurry of memos from 1962, which revealed an interest to include a Tektronix 321 oscilloscope in the Apollo lunar module. Investigation revealed the 321 would not meet the strenuous vibration and acceleration force at liftoff, and Tektronix concluded that ruggedizing the 321 was not feasible because of the size of the effort. In April 1962, North American Aviation indicated they definitely wanted an oscilloscope in the lunar module. The oscilloscope was thought to be needed for use outside the vehicle for repairs on the lunar surface. As we all know, the Apollo program succeeded in landing on the moon without a Tektronix oscilloscope, but it must have been an interesting set of conversations. The Type 422 oscilloscope was another step forward in small portable instruments. It first appeared in the 1965 Tektronix catalog. It is a dual-trace 15 MHz portable oscilloscope ideal for field service work. It used Tektronix's first CRT with a scan expansion mesh to allow a 4-inch diagonal screen size of the shorter package. The CRT also utilized a low-power cathode and was initially fabricated with a glass funnel, which was later converted to ceramic. The AC model could be powered from 115 or 230 volts AC, 45 to 440 Hz. 400 Hz power is commonly used in aircraft, spacecraft, submarines, and other military applications. The AC-DC model could also be powered from 11.5 to 35 volts DC. There was also a 24-volt battery pack available. The selling price was $1,325 when equipped with the AC-only power supply, and appeared in the catalog from 1965 to 1975. Tektronix oscilloscopes have been essential to the development and maintenance of IBM computers. For a time, the Tektronix 310 was a standard IBM service tool, being small enough for IBM service engineers to carry to customer premises. At larger accounts, IBM would often leave a Tektronix instrument permanently. An IBM-owned Tektronix 554 was a permanent resident of Caltech's Booth Computer Center in the 1960s. With the introduction of the IBM 360 series computers in 1965, IBM needed a portable oscilloscope with speed and capabilities to match the more complex architectures. This called for dual vertical inputs, a bandwidth of 50 MHz, and fast dual sweeps. Tektronix responded to IBM's request with the 453. One key requirement was that the instrument needed to fit under an airline seat. Fitting all those requirements into a small portable instrument was a considerable challenge. Fitting all the controls on the front panel to allow convenient operation was a key concern. Tektronix developed a gear shift sweep knob, which in essence is 3 controls in one. The user could pull the main knob to operate independently of the rear portion of the control, to allow operation of both sweeps with a single knob. The first scope cart was a Type 500, designed for the 517 oscilloscope. The 517 was comprised of 2 pieces and weighed 175 pounds. The 500 scopemobile shown on the left with the smaller 541 oscilloscope enabled these larger instruments to be more portable. Gail Morris Type 200 scopemobile design is shown on the right and was in the catalog for a number of years. It was shown at the 1961 Westcon trade show and won approval from the judges at the 3rd Annual Industrial Design Award Program. It was among 23 entries selected for the Award of Merit and was one of the 5 products chosen for the Award of Excellence. Gail Morris would visit the museum and donated copies of 2 of his original hand drawings of a scopemobile, one of which is shown here. These are amazing drawings with intricate detail all done by hand with brushes, pencils, and airbrushes. Gail eventually headed up the Industrial Design Group, and they greatly influenced the 7000 series introduced in 1969. Gail made a presentation of the usability features of the 7000 series at the product launch meeting for the worldwide sales force. He kindly recreated this presentation in the video we have on the museum's video gallery. Howard Vollen thought that a new line of miniature oscilloscopes would expand the market. The key challenges to such an instrument were a low-power CRT, integrated circuits to minimize power and size, and a small package. The first handheld concept prototypes were simple cardboard models made by the Industrial Design Group. Challenges were overcome and the first miniscope, the 211, was introduced in 1971. It was promoted as the first laboratory-featured miniscope. It had a single channel with 500 kHz bandwidth, weighed a mere 3 pounds, would operate for 5 hours on its internal batteries, and was designed for severe environments. It was soon followed by the dual-channel 212 and the dual-channel storage miniscope, the 214. The 221, introduced in 1973, increased the bandwidth to 5 MHz. The 213 DMM miniscope was introduced in 1975 and included digital multimeter functions which displayed on the CRT, and was selected by Industrial Research as one of the 100 most significant new technical products of 1975. A time-domain reflectometer, known as a TDR, is similar in principle to radar for detecting discontinuities, breaks, and other anomalies in metallic cables. The TDR transmits a step pulse in the cable and listens for a reflection. If the cable is properly terminated, the pulse will be fully absorbed and there will be no reflection. Any discontinuity will cause a reflection, which is added or subtracted, thus distorting the step pulse. The round-trip time can then be measured, and using the speed of propagation in the cable, the discontinuity can be pinpointed with extreme accuracy. The 1501 is a compact TDR with an internal printer introduced in 1971. It had to be mated with a compact 323 oscilloscope to provide a real-time view. The 1502 shown here integrated all the elements together into a ruggedized package for field use. It was introduced in 1976 for a price of $3,360. The 1502 can resolve to 0.6 of an inch at distances up to 2,000 feet. We often demonstrate this instrument to our younger visitors and calculate the speed of propagation in the cable at 124,827 miles per second. Oscilloscopes generally display electrical signals with respect to time. The TDR just seen displays electrical signals with respect to distance. A spectrum analyzer displays electrical signals with respect to frequency. The first spectrum analyzer associated with Tektronix instruments was a plug-in designed by a company called Tektronix and introduced in 1964. Tektronix acquired Tektronix in 1964. The three founders moved to Beaverton and continued to develop a number of spectrum analyzer plugins. In 1967, Tektronix introduced the 491 portable spectrum analyzer. Although the 491 required an expert user and had limited capability, it moved microwave measurements into the field, and many units were sold to those servicing radar systems. In 1971, Tektronix introduced the 1401, a small and moderately easy-to-use spectrum analyzer. This instrument was the same size and shape as the 323 Sony Tech oscilloscope, which was used as the display portion. It was small and truly portable, operating on batteries or AC. The 496 spectrum analyzer shown here was introduced in 1981. Our exhibit in the museum is configured with a tracking generator, which allows display of the frequency characteristics of components or systems.